Hey everybody, it's Mr. Carr again. Today we're looking at 10-3 day one. We're going to move on from our arithmetic sequences for a bit. Instead, we're going to talk about what's called geometric sequences. Just like before, we're going to be talking about an explicit and recursive rule with these, as well as what our geometric means. Okay, so let's take a look at an example of a geometric sequence here. So geometric sequences are ones that have a common ratio instead of a difference. We use R to represent that common ratio. So one way we can always find R is going to look something like this. It is the ratio of consecutive terms. So just like we did before with common difference, where we took a term minus the one previous to it, we're going to take the ratio of a term divided by the one right before it. Okay, so this means we take any term in the sequence and divide by the previous term. So one thing that's going to be interesting about this is that geometric sequences are very much like exponential functions. They have a very similar behavior with them compared to kind of like arithmetic is very much like a linear situation. Geometric is like an exponential. So let's look at this as an example of one right here. So you notice that this pattern goes negative, positive, negative. That means my ratio, my common ratio, has to be a negative number because that's the only way I'm going to swap back and forth between the two. And then my next step is I got to figure out, well, how can I get from -6 to 9? And how do I get from 9 to -13.5? If you don't see it right away, you can do any term divided by the previous term. So it's -9/6, which is -3/2. So that's my common ratio here. So if I multiply by a -3/2, I get from -6 to 9. If I multiply that by -3/2, that's also going to get me to the next number of -13.5. Okay. So another example of that. Determine the common ratio and find the next three terms of the geometric sequence here. So we have 243n minus 729. So we got two things going on at once, and especially with that n there kind of throwing us off. So again, focus on any one of these at a time. So how can I get from 243 down to -81? Okay, so if I look at that as -81 divided by 243, okay, so -81 divided by 243, it's going to give me a -1/3. So that is the value that I'm multiplying to everything here. So if I multiply by a -1/3, but I do it to both of these, that gets me to the next thing. Okay, this multiplied by -1/3 gives me a positive 243. When I take this times -1/3, I get positive 27n. So my common ratio here is -1/3. Just looks a little bit weird with the extra like kind of formula in there. So this is identifying our common ratios. We can also use that in our explicit rule. So when we write an explicit rule in terms of the nth term, so a sub n, it's always going to be, we start with our first term a sub 1 and a common ratio r. It follows this formula. A sub n is equal to a sub 1 multiplied by r raised to the n minus 1. Okay, so it's always going to follow that pattern. Now, does it come up with recursive? Yeah, it does come up with recursive. So we'll talk about the recursive when we get to the next problem. So the idea again is that we can jump to any term we want in a sequence by using this formula. So if I have this right here, we establish that it's times 5 times 5. There's my common ratio. I want the ninth terms. We're going to put the 9 minus 1 up here. We start with the first term here is 2. That's how we get to the value of 781,250. Okay, so let's write the rule out for this sequence here, and as well as recursive one. So for here, we got to first figure out what is my common ratio. So again, if I have trouble with that, I can take any sequence or any term divided by the previous term. So in this case, it's just -2. A sub 1 is -1. So that means I can write a sub n is equal to a -1 times r, which is -2, raised to the n minus 1 power. There's my explicit rule. Okay. My recursive rule, think about what's happening in each case. For my recursive rule for geometric, any term in the sequence is coming from the fact that we're multiplying the previous term by a common ratio. And we usually do it this way. We'll do a sub n minus 1 multiplied by r. So just like we did with arithmetic sequences, we also want to say, where does the pattern start from? Where is a sub 1? So in this specific case, we can say that a sub n is equal to a sub n minus 1 multiplied by a -2, with a sub 1 being -1. Okay, so again, any term in the sequence is the previous term multiplied by a -2. That's what that's stating there. All right. So in this case, we're again, just like before, we want to first establish our explicit rule. That's what's going to help us find the 11th term here. So if I want to find my common ratio, I'm going to take 115.9 divided by -122. So if I do that, 115.9 divided by -122, and I get -0.95. Okay, doesn't matter if I put a decimal in there, it's still the same thing. So I've got my common ratio. I've got my first term is -122. So my explicit rule is going to be -122 multiplied by -0.95 raised to the n minus 1. So if I want the 11th term, that's going to be -122 times a -0.95 raised to the 11 minus 1 power. So from here, it's just a matter of making sure you plug it into your calculator properly, doing your order of operations, subtract that first to make it a 10. So -122 times -0.95 raised to the 10th power. It's going to give me -73.046. Just go 3 decimal places for that one. Okay. A couple purchases a home for $225,000. At the end of each year, the value of the home appreciates 3%. Write an explicit formula for finding the value of the home after n years. So this is another one where, so this is one where it's appreciating. So with this 3%, it's kind of like with our exponential rules. So if it appreciates by 3%, what's happening is my common ratio is going to be 1 plus the 0.03 to get to 1.03. Okay, that's how much it's going to grow each year. So 225,000 is going to be a little bit tricky on this one. So let's see, we're probably going to have to, after the end of the 10th year, give me 1 second on this one. Okay, so the way this is worded is a little bit tricky when we compare it to like exponential formula. So let's look at this one. Again, we always put it in terms of a sub 1. That's what we've been doing in this one. So I'm going to define a sub 1 as being the 225,000 multiplied by 1.03, because this is what happens after the end of the first year. Okay, so if I do that, 225,000 times 1.03 is going to give me 231,750. So now I have enough to write my formula. A sub n is equal to 231,750 multiplied by the common ratio of 1.03 raised to the n minus 1 power. So for part B, finding the value after the 10th year, now I can do a sub 10. So again, I define this as this is the end of the first year. It's going to be valued at 231,750. Okay, the end of the first year. This is going to be the end of the 10th year. So 231,750 times 1.03 raised to the 10 minus 1 power. Okay, so I've got that. 1.03 raised to the 9th power. And that's going to give me 302,381 and 19 cents. So that's the value of the house after at the end of the 10th year. Okay, so again, that's that after the 10th year. So $302,000 basically. All right, one last thing to cover, and that's going to be geometric means. This works exactly the same way as arithmetic means. This is the first term. This is the last term. So what we have is 264 is at the beginning. There's 3 geometric means. So it's going to be 1, 2, 3 spaces in between. And it finishes with a 1.03125. So this one's a little bit trickier, but here's what's happening. If I model what's happening at each of these steps, we are multiplying it by a common ratio r at each time. So basically, we know that if we take 264 and we multiply that by r to the 4th power, because we have 4 common ratios being multiplied through, That will result in 1.03125. So now we just got to work this backwards and undo this to get the common ratio. So if we divide both sides by 264, so R of the fourth will be 1.03125 divided by 264. .003906. And then I'll take the fourth root of that. And I get, again, I didn't round it off in my calculator. I used the previous number, but I get 0.25 for my common ratio. Okay, so that means I can write this out now. It's going to be A sub n is equal to my first term, 264, multiplied by the common ratio of 0.25, raised to the n minus 1 power. So again, geometric means are going to be representing those missing terms that are in between what's given. Okay. That's it for today. Again, geometric sequences have their own recursive and explicit rules based on a common ratio, but we're still going to do it in terms of the first term. Okay. And then those geometric means can also be used in between those two given sets of numbers. All right. That's it for today. Take care, everyone.